All right. Yeah, I've shared my screen. Let's start the session. Hello, everyone. Welcome to the weekly discussion and downloading session number 4 of the NPTEL course on concrete technology, NOC24-CE46, which is taken by Professor B. Bhattacharya of IIT Delhi. I'm Ashirpad Satpathy. I'm a PMRF research scholar from IIT Delhi, and what I do is I take these weekly sessions where we discuss the uh, practice problems or the assignment problems of the previous weeks that you have already submitted the answers to, and the deadline has already passed. And we also take up any of the doubts that you might be having regarding the previous week's lectures. I'm also the officially assigned teaching assistant for this course. I usually take my sessions, these weekly sessions of 2 hours on Mondays from 6 to 8 p.m. And there is another teaching assistant to this course. His name is Debojyoti. He usually takes his sessions on um, Saturdays from 6 to 8 p.m. All right. In today's session, we'll be discussing the assignment 3 problems of the week 3 lectures. And this week 3 lectures were more or less about um, the different types of aggregates and the roundness of aggregates, the fineness of aggregates, and how it these values, the fineness of aggregates, how they affect the packing density of given aggregate mixture, and what happens to the packing density and void ratio when we add aggregates of different sizes to um, a given mixture. And at the end of the session, we'll be taking any of the doubts that you might be having regarding the week 3 lectures. So the first question was the packing density of a single-sized spheres is, and the given options were less than 0.52, more than 0.74, lies between 0.52 and 0.74, and none of the above. Which of these options is correct related to the packing density of single-sized spheres? Yes? Can anybody answer to this question? Right? Um, so the correct answer to this question is actually it lies between 0.52 and 0.74. And as we know that when we are considering spheres and we are considering a 3D geometry of packing, I mean the crystal lattice, we are there are three basic crystal lattice packing structures that can be assumed. One is a simple cubic structures. Simple cubic structure meaning it has spheres, spheres at corners only, right? This is the basic lattice structure or the lattice system that we talk about. It's a simple cubic structure. Then comes a body-centered cubic structure or BCC, body-centered cubic structure, which is also called BCC, and this basically has spheres at corners and one at the body center. And finally, the third one is face-centered cubic structure. In case of face-centered cubic structure or FCC, as we call it, it has spheres at all the corners, and then it has again uh, spheres at the faces. So the spheres that are at the corners, that those are shared by four of these lattice unit cells, while the spheres that are present at the faces of the system or of the cube, those are shared by two of these unit cells, right? And if we consider the, I mean, if we compare the packing efficiency of these three different types of crystal systems, we know that the packing efficiency of the simple cubic structure is the least, which is 52.4%. The body-centered cubic lies between. All right, due to some uh, technical issues, the session could not be recorded for the whole duration of the meeting. So I'm recording this session at a later stage and attaching it to the original video. So basically what we are discussing is the packing density of single-sized spheres, and these are the three basic lattice packing systems: the simple cubic system, the body-centered cubic system, and the face-centered cubic system. And we know that the packing efficiency in these systems are 52.4%, 68%, and 74% respectively. So whenever we are considering any system of single-sized spheres, then the packing density of that system has to lie within these values, 0.52 to 0.74. So the correct answer to this question was the third option, right? Moving on to the second question, if E is the void ratio of a binary mixture of aggregates, what will be its packing density? And the important phrase in this question is binary mixture. So basically, we're mixing two different sized aggregates in a given mixture, and as we know that void ratio E, as we represent it, is the ratio of volume of voids to the volume of solids. So that will be equal to VV by Vs. Let this be equation 1, and we know that again the total volume V is equal to the volume of solids plus the volume of voids. So let this be equation 2, and from equation 1 and 2 we know that the volume of voids is equal to V minus Vs, and therefore if we substitute this value in the original equation 1, which is E, the void ratio, we'll know that the void ratio is V divided by Vs minus 1. Now, packing density, what is packing density? It is the ratio of the solid fraction volume to the total volume. So it is equal to Vs by V. Now, from equation 3 and 4, we're able to know that void ratio E is equal to 1 by packing density minus 1. So the packing density comes out to be 1 by E plus 1. So the correct answer to this question was option 3, 1 by E plus 1. Right? The third question of this assignment was for a binary mixture. Again, it's a mixture of two different sized aggregates. For a binary mixture, which of the following is true for the packing density? Packing density increases with addition of second size. Packing density decreases with addition of a second size. Packing density increases initially but starts decreasing after a limit. And the packing density remains constant. And we discussed that in the lecture as well. So packing density doesn't remain constant, that's for sure, because as we keep on adding two different size spheres, let us say there is a system of single size spheres of coarser material. So the spheres are larger in size, and now we're adding a second system of smaller sized spheres to this original system. What will happen? The smaller sized spheres will take up the voids of the largest sphere system, right? So then the void ratio will decrease, the volume of voids will decrease, and the void ratio will decrease. And when the void ratio will decrease, as we know from the previous question, the packing density will increase. Now, so this is for sure, packing density doesn't remain constant. As for the first two options, packing density increases with the addition of a second size or decreases with the addition of a second size, we take the help of this view graph, which plots the packing density versus the volume size fraction of two different sized aggregates. Let us say there is a system of aggregates of size A, let this be A, and there's another system of aggregates of a different size. Both are single size aggregates. Let A be a coarser aggregate system and B be a finer aggregate system. And so the second aggregate system is B, and at this point in the x-axis, if we mark the x-axis as the volume fraction of B to A, meaning that x star at any given point is equal to the volume of solids of B divided by volume of solids of A in the total binary mixture, then we'll see that at x equals to 0, meaning that B is equal to 0 at this point, and it is a single system of A sized aggregates, and at x equal to 1, it will be a single system of B sized aggregates, and at any intermediate x star value, solid fraction value, we'll see that the packing density initially increases, meaning that when we keep on adding B system to the A system, it initially increases, reaches a summit value, a highest peak value, and then further decreases. So whenever there is a single sized sphere, the packing density is low, but as we keep on increasing the different modes of different sized aggregates, meaning that as we keep on adding different sized aggregates to the original system, it increases the packing density to a certain value. But further, if we keep on adding the aggregates, then it will further decrease the packing density. Let us say, for example, there's a coarse particle system and we are adding finer particles to it. Now, initially, the finer particles take up the void spaces inside the coarse particle system, but and the total volume is not increased for a given state. Now, as we keep on adding these finer particles, the void ratio decreases, but the total volume remains same, and these smaller particles take up the void spaces. But when we reach a certain limit, which is called as the maximum packing density of the system, as we keep on further adding the smaller particles to the system, these there won't be any void spaces available for these particles to take up, and therefore they will add up to the total volume of the system, and thereby the packing density will decrease, right? So in this view graph also we saw that two different curves of packing density, how it varies with the solid volume fraction, has been shown. The blue curve is the ideal curve, meaning that it should increase linearly and then decrease linearly. But in practicality, it doesn't happen so. The the packing density has a curvilinear approach, has a curvilinear behavior. And why does this happen? This happens due to two effects. The first one is the wall effect, and the second one is the loosening effect. What is the wall effect? In an ideal system, we are assuming that when we are adding finer particles to a core system, they're taking up all the void spaces in the best possible manner, right? But practically, what happens is, if there is a large aggregate like this, and the smaller particles are arranged at the surface of this aggregates, they do not have the best possible packing within the smaller particles, and due to the irregular shape of the particles and due to the wall that they're facing from the coarse aggregate, there are large void spaces remaining in between the finer particles, and therefore the packing density decreases due to this wall effect. Again, what is loosening effect? Whenever there is a small particle trapped in between larger or coarser particles, it tries to push the coarser particles further apart in order to take up that void space, and therefore the packing density, instead of decreasing, it increases by a certain value, because the smaller particles are pushing the um, coarser particles further apart, and instead of taking the amount of volume that they should ideally be taking, they're taking a larger volume than that. So the packing density further decreases. So therefore, you see that the practical packing density curve, or the practical maximum packing density, is lesser than the ideal maximum particle density, packing density. This is because of these two effects, the wall effect and the loosening effect. All right. Moving on to the fourth question. The fourth question was, for single-sized particles of size 300 micron, fineness modulus will be. And again, the important phrase in this question is single-sized particles. So the correct answer to this question was 2. And then we discussed how the sieve sizes or the sieve numbers have been obtained from sieve sizes. So we know that the sieve sizes have been chosen in a certain way such that all the sizes are in a geometric progression. Now, in order to plot the values in a arithmetic manner, we have to convert these values of geometric progression to arithmetic progression, and for that we take the logarithm of these sieve sizes. So we explained that the lowest sieve size is 75 micron, then 150 micron, 300 micron, and so on. And if we consider the log of 0.075 mm, and then we consider the log of 0.15, then log of 0.15 is log of 0.075 into 2, which gives us log of 0.05 plus log 2. Again, moving on to log of zero point 0.3, it will give us log of 0.075 into 4, which will give us log of 0.075 plus 2 log 2. So you see that the progression is such that it is a, then a plus d, then a plus 2d, a plus 3d, and so on. So the values are now in an arithmetic progression, and now we can plot them in a xy graph. Now, in order to calculate the fineness modulus, we have seen this in the lecture as well. I'll just open up the lecture file. Yes. Yeah. So it has been mentioned in the lecture that for single-sized particles, the fineness modulus of ith size is the sieve number itself, that is 1 into I. And we know that 75 micron sieve is numbered as 0, 150 micron is numbered as 1, and 300 micron is numbered as 2. So the fineness modulus of single-sized spheres of 300 microns will be 2. So the correct answer to this question is 2. Right? So in order to explain how we arrive at this 2 value, I'll take the help of this uh, I'll again take the help of this lecture slide. So basically we know that the fineness modulus is the total cumulative percent retained on each of the sieve sizes and the sum of that divided by 100, right? And if we just expand this equation, we'll see that Fm is equal to 0 into P0, P0, P1, P2, P3 being the amount of material retained at a given size, meaning that let us say X amount of material passes through 300 micron and Y amount of material passes through 150 micron. Then what will be the P corresponding to 150 micron? It will be X minus Y. So the particle fraction that is retained on a given sieve, that is known as the particle fraction corresponding to each of the sieve numbers, is P0, P1, P2, P3. And if you see the expression of fineness modulus, you'll see that 0 into P0 plus 1 into P1 plus 2 into P2 and so on. And we know that the particle fraction for the 300 sieve in this system, in this system of a single-sized spheres, it is 100% because all of the particles are of the same size, that is of 300 microns. So all of them will be retained on 300 sieve, and therefore it will be 2. The particle fraction will be 1, so it will be 2 into 1, and rest all the numbers will be 0. So the fineness modulus will come out to be 2. So this is how we came at this expression. All right. Moving on to the fifth question, this is very straightforward. Which of the following property of aggregate is related to the volume changes due to wetting, drying, thermal, and frost action? And we have also discussed this in detail in case of cement as well. What causes deleterious or excessive volume expansion in the cement? That is called as the unsoundness of cement, and that is caused due to maybe lime or excessive sulfates or excessive magnesia in the cement. So that causes the unsoundness in cement. But in the case of aggregates, these volume changes, again, whenever there is excessive volume change, that is due to unsoundness. So the property that is related to the volume changes due to wetting, drying, and thermal or frost action is the soundness of the aggregates. So we test the soundness of aggregates in order to know if the aggregates are going to undergo a lot of volume changes due to these actions, environmental exposure conditions of wetting and drying, or very high temperature conditions, or very low temperature conditions due to frost. All right, moving on to the sixth question of this assignment. Calculate the specific surface in cm square per cm cube or centimeter square per centimeter cube for the given grading of rounded aggregates. And in a table, the sieve sizes have been given, and the percentage passing for each of the sieve sizes have also been mentioned. And we have to calculate the specific surface. Now, in order to calculate the specific surface of, and it has been mentioned that these are rounded aggregates, so we are to assume that these are spherical particles. So when it is rounded aggregates, we are assuming that they are, the assumption here will be spherical particles, right? So in order to calculate the specific surface area, let us see what all parameters do you need, and for this I'll take the help of the lecture slides. So specific surface area can be related to the surface modulus, as it has been mentioned. It has been also taught to you in the lecture as well. It is related to the surface modulus. How? The specific surface area for a sphere is 6 by di, because it is specific surface is area by volume, right? So the specific surface area of sphere is 4 pi r, or 4 pi d cube, 4 pi d square by 4, and then the volume of a sphere is 4 by 3 pi d cube into 1 by 8, right? And so this 4 goes away, and this is 2, so what we get is, and then 3 go, pi and pi go, so it is 6 by d for a given size, and for ith size particle it is 6 by di, right? So the specific surface of a single sphere is 6 by di. Now for two sieve sizes, let's say di and di minus 1, the specific surface will be the 6 divided by the geometric mean size, which will be equal to 6 divided by root over of di into di minus 1, right? Now we know that since the particle sizes, as they increase, the specific surface will reduce by factor of 2. When this particle sizes increase, it is a known fact that the specific surface will also decrease, and it reduces by a factor of 2. Now, in order to find out the specific surface of a given sieve size distribution, we need to know the surface modulus. How do you calculate the surface modulus? It is given by this formula. Just erase this. So the surface modulus is given by this formula. Sm is equal to P0 plus P1 by 2, P2 by 4, dot 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 Pn by 2n. What are P0, P1, P2, and Pn? P0 is uh, particle sizes, particles around 75 microns. All right. Similarly, P1, as we know that the sieve sizes have been um, named as 0, 1, 2. So 75 micron is 0. Particle sizes around 150 micron is P1, and so on. Right. So in order to calculate the specific surface, we need to know the surface modulus. And in order to calculate the surface modulus, we need to know the particles retained on each of these sieves. And we have been given with this table, which shows the percentage passing on each of these sieve sizes. So we can also calculate that. All right. Then what do we do with the surface modulus? So once we got the surface modulus, the specific surface can be calculated as, so here it has been given as an example. Let's say we have only two sieve sizes, sieves, so 0 and 1. So the specific surface will be 6 divided by 0.0075 into 0.015, and these are in cm, centimeters, right? So in centimeters, it has been given. So for sieve sizes 0 and 1, it will be 565.7. 6 divided by, so this will be divided by, this is again divided by, yeah. Again for sieve sizes 1 and 2, so it will be 6 divided by 0.015 and 0.03 root over. So that will be 565.7 divided by C2. So you can see that if we take 565.7, this factor as common, will be left with what we call as the surface modulus. So in order to calculate the specific surface, we need to multiply the surface modulus with this value, right? So how do we calculate that then? So first of all, we'll calculate the amount of particles ranging between 10 and 20, 10 and 4.75, 4.75 and 2.36. So we have to calculate the particles in this manner. All right. So let's do that. So P0 will be P0 particles sizes. Let me just erase this first. So let's start with particle sizes. Then we'll have sieve sizes. And then we'll have percentage of particles. So for P0, what are the sieve sizes? Those are 0.075. I'm mentioning this in mm right now, and 0.15. So what are the particles sizes retained? So 0.075, it is 0. So we have 1 minus 0 is equal to 1. For P1, it is 0.15 and 0.3. What are the particle sizes retained? It will be 10 minus 1, that is 9. For P2, it is 0.3 and 0.6. So that will be 25 minus 10, 15. For P3, it will be 0.6 and 1.18. So that will be 30 minus 25. You see that 30% of the particles pass through 1.18, and then 25% of the particles pass through 0.6. So the amount retained between 0.6 and 1.18 will be 30 minus 25. So we're doing calculating that amount, so that this will be 5. Then P4 will be 1.18 and 2.36. So that will be 35 minus 30 is equal to 5. P5 will be 2.36 and 4.75. So that will be 40 minus 35 is equal to 5. And then P6 will be 4.75 and 10, and that will be 75 minus 40, so 35. And finally P7 will be 10 and 20, so that will be 100 minus 75, which will be 25. So these are the values we have been given with for P1, P0 till P7, right? And we have calculated the percentage of the particles around these sizes. Now, in order to calculate the surface modulus, what we'll do is surface modulus Sm is equal to, so what is the formula for surface modulus? P0 plus P1 by 2 plus P2 by 4 and so on. So it is P0 plus P1 by 2 plus P2 by 4 plus P3 by 8 plus P4 by 16 plus P5 by 32 plus P6 by 64 plus P7 by 128. So let's calculate the surface modulus now. So the surface modulus will be P0 is 1 plus 9 divided by 2 plus 15 divided by 4 plus 5 divided by 8 plus 5 divided by 16 plus 5 divided by 32 plus P6 is 35. 35 divided by 64 plus P7 is 25 divided by 128. And this gives us the value of 11.08, right? So surface modulus is 11.08. 0.086, and this will come in percentage. And then if in order to calculate the specific surface, so specific surface will be, it's not actually in percentage, it will be in fact alright, we'll just forget about the units because it will be, we have assigned the units to the value of 565.72. So we'll just calculate the final. Yeah, I mean surface modulus will come in percentage, of course, but in order to calculate the specific surface, we have to convert it into cm square plus per cm cube, and already we have taken care of the units in the factor of 565.7, as you have seen over here. All right. So this is the factor we have taken. So here we have taken cm square per cm cube. So this will give us the final result in cm square per cm cube. Um, yes, so that will be 565.7 specific surface is equal to 565.7 into SM equal to 565.7 into 11.086. So this will give us the value of, so the answer to this question is 6,271. 6,271.3 cm square per cm cube. So this is the correct answer, right? So this is how you calculate the specific surface and the surface modulus of a given sieve sizes distribution. Hope that was clear. Moving on to the seventh question. For the above given grading of rounded aggregates, find the fineness modulus. How do you find the fineness modulus of, again, it is the same sieve size distribution that has been taken from the previous question. So I've mentioned it in the right section. So what is how do you calculate the fineness modulus? Let us see in the lecture slides. So fineness modulus is calculated. We had also discussed previously how fineness varies as a factor. So these sieve sizes vary by a factor of 2, and so they lie in a geometric mean kind of a fashion in order to plot them in x and y axis. So for we have to convert the geometric mean in geometric progression to arithmetic progression, and in order to do that we apply a logarithm to these sieve sizes, and thereby we get the log of these sieve sizes and plot them in the x and y axis. So we had already discussed that previously. The fineness modulus is calculated as follows. So this is 0 into P0 plus 1 into P1 plus 2 into P2 and so on. Then again 0 into P0 plus 1 into P1 plus 1 into P2 plus 1 into P3 and so on. Then there will be 1 into P2 plus 1 into P3 and so on. So here what we are doing is we are finding the cumulative percent retained for all the sieve sizes. So it is 1 divided by 100 of cumulative percentage retained on sieve 1, cumulative percentage retained on sieve 2, sieve size 3, and so on till the highest number of sieves. So it is, so fineness modulus can be called as the summation of the cumulative percentage retained on each of the sieve sizes. So this is the sum of the cumulative percentage retained on each of the sieve sizes divided by 100. So in order to calculate this question, so here we have plotted the table of the cumulative weight retained on each of the sieve sizes. So for 20 mm sieve size, 100% of the material is passing through it, so the cumulative weight retained is 0, right? For 10 mm sieve size, only 75% of the material is retained, so it is 25% retained. For 4.75 sieve size, 40% of the material is passing, so all 60% is retained. And then for 2.36, only 35 is passing, so 65 is retained, and so on, right? And then we find the sum of all these cumulative percentage retained on each of the sieve sizes, and that comes out to be 484. Now fineness modulus is 4. It is the summation of cumulative weight percentage retained
on all the seed size. So this is the summation sign divided by 100. So fineness modulus is 484 divided by 100. This will give you the value of 4.84. So that's the answer to this question. So yeah, that was the end of the assignment 4 of week 4. I'm sorry to say that we could not do this live. I had some technical issues on my side, so therefore I'm recording this session at a later date and I'm uploading it for now. So thank you.